Hello, everyone, and welcome back. My name is Mr. Cobalt, and in this video, I'm going to go over hybridization of orbitals and how that relates to the shape of molecules. And so, the way you want to think about hybridization, you want to think of it as a blending of the orbitals. So, just like in a blending, if you mate two dogs together, like a poodle and a Labrador, when you blend those together, you'll get what is called a Labradoodle, right? So you get something from both of them that has similar characteristics of both. So that's kind of like the hybridization of the orbitals. So it's analogous, not exactly what's going on, but it's kind of a good analogy. And so when we're talking about hybridization of orbitals, this is where we're going to be combining two or more different orbitals that have similar energy, and you're going to spit out or get from those orbitals um, equal energy orbitals that is kind of a mixture of both. So you take orbitals, different orbitals, you hybridize them, and you get the same number of orbitals, but they are a hybrid of the orbitals you had mixed together. So what do I mean? Let's show you how this is done. All right, so here um, there's an s orbital and you have a p orbital. And so this is called, we're going to talk about what is called sp hybridization. And this is where you take an s orbital and you take a p orbital and you hybridize them together. And notice that you start with two different orbitals. And when you hybridize them, you get two orbitals back out. So the number of orbitals you put in gives you the same number of orbitals you get out, but the two orbitals that you get are now hybridized orbital. So here you have an s orbital and a p orbital. These are not the same energy. They are different in energy. But when you hybridize them, you get two equal energy orbitals. So now you get what are called sp hybrid orbitals. So you get these new orbitals, and these are the orbitals that are formed that are involved in bonding. So this comes from a theory called valence bond theory. And so in valence bond theory, whenever you have atoms coming together and bonding, the orbitals will hybridize. So the orbitals that the atom has, and these are specifically the valence orbitals, so usually s and p, some d orbitals too. But these orbitals that are involved in bonding are going to hybridize in the atom itself. So the atom has its orbitals hybridized, and you get these new orbitals that are all equal energy. And then what happens is that these new orbitals with the electrons, so the electrons are occupying these hybrid orbitals. And again, using VSEPR theory, the electrons want to repel each other, and they're going to try to get as far apart as possible. And depending on the number of hybrid orbitals you have, that will determine the shape of your molecule. So here we have two hybrid orbitals. So those two, the electrons that are forming those orbitals, or those electrons that are occupying these orbitals, are going to want to be as far apart as possible. And so when we look at the an atom, so here we would have the central atom here in the middle, and then the orbitals, right? Here are the orbitals. So you have one hybrid orbital here. This would be one sp hybrid orbital, and this would be another sp hybrid orbital. And this is where the atoms would be overlapping. So you'd have an atom here that would be overlapping with this orbital to form a bond. And then you'd have an atom over here forming a bond here. And so you'd get a 180 degrees. So these electrons from this bond would be on this side, and the electrons in this orbital would be on this side, forming a bond. And so you get this 180 shape. And so this would be a linear molecule. So again, one s orbital is going to combine with one p orbital, and you get two p orbitals are left, and they are the same. So remember, you have three p orbitals, the px, the py, pz, and you're taking one of those p orbitals and you're combining it with an s orbital, and that's going to leave behind the other two p orbitals are left, and they're left the way they are. So this is what it looks like here. So here you have the orbitals, and so you've got the s orbital here, and then at a little bit higher energy, you have the 3p orbitals. So what happens during bonding, so the central atom, the orbitals, when they are bonding, let's say there's going to be two bonds, or you need two electron groups. If there's two electron groups, then you take an s orbital, the 2s and the 2p. Those are going to hybridize, right? And then remember what I said before. Whatever you put in, that's what you get out. So if you put two orbitals in, you get two hybrid orbitals out. And so here you're taking an s orbital and you're taking one of the p. And over here, when you do the hybridization, notice you got the sp. You got two sp hybrid orbitals. And notice that the two sp hybrid orbitals are a little bit higher in energy than the s, but they're lower in energy than the 2p. So the hybridized orbitals are somewhere in between your s and your p. So now you have two hybrid orbitals. These two hybrid orbitals, the sp hybrid orbitals, are going to be involved in bonding or in having electron groups. And the other two orbitals are left by themselves. So these are the unhybridized p orbitals. And a lot of times the unhybridized p orbitals is what is used to form your double and your triple bonds, but we won't get into that too much. So here's a picture. You got these. You got the s and the p. So maybe these two orbitals are going to form your two hybrid, and so you get the two hybrid orbitals here, and then you've got your unhybridized p orbitals that can be involved in double and triple bonds. So there's these, and these two here are going to form the hybrid orbitals, and that's what you see here. All right, so next is sp2 hybridized. So the 2 here means that you're using two p orbitals. So before, with the s and the p, the sp hybrid orbitals, that's where you had one s and one p. But with the sp2, now you're going to have one s, and you're going to hybridize that with two p orbitals. So you got a total of 3 orbitals coming in, and then you're going to form 3 hybrid orbitals. So this is what it looks like here. So these 3 orbitals here, so you've got the 2s and these 2p orbitals. You're going to take those and you're going to hybridize those. And since you're taking 3 unhybridized orbitals, and then you're making the hybrid orbitals, you're going to get 3 sp2 hybrid orbitals. And again, these 3 orbitals are going to be involved in bonding and lone pairs. So the pairs of electrons that are on your molecule are going to be involving the sp2 orbitals. And since you got those hybrid orbitals, you got 3 of them, then that's going to allow it to have a certain shape, like a trigonal planar shape. And so here's again a picture of it down here. So you have your s orbital, and it's going to hybridize with 2 p orbitals, and then you get the 3 hybrid orbitals here. So you take 3 unhybridized orbitals and you get 3 hybridized orbitals. And so you can see again that the 3 sp2 hybrid orbitals are in an energy, they have a higher energy than the 2s, but they have lower energy than the 2p. So again, they're somewhere in between the s and the p. So they're hybridized in energy as well. And then the sp3 hybrid orbitals, again, that's where you take an s orbital and you take 3 p orbitals, all 3 p orbitals, and you mix them together and you get 4 sp3 hybridized orbitals. So again, here we're going to take all 4 orbitals and we're going to hybridize them into 4 equal energy sp3 orbitals. And again, the equal energy sp3 orbitals are between, they have an energy that's between the s, higher than the 2s, but lower than the 2p. So here again, we're going to take these 4, and this is the picture of them. So we're taking the s and the 3p, and we're going to hybridize them, and we get these 4 equal energy hybrid orbitals. And that's what we see here. So the energy is behind. So that's what the the hybridization does for the orbitals. So again, the idea, if we're going to link this to VSEPR, the VSEPR theory is a theory of electron repulsion. So electrons are going to repel each other to get as far apart as possible, and that's going to allow the shape. But then you got to think about, well, where are the orbitals? Well, that's where the hybridized orbitals come in. So if you have hybridized orbitals, that allows you to have the electrons in those hybridized orbitals, and you can then spread those orbitals out. The electrons can repel each other, and you get that shape. Without the hybridization, it would be hard to get a shape like a tetrahedral shape, or um, or any of the other shapes, like with 120 degrees, like the trigonal planar shape, because as we saw before, the p orbitals, the px, the py, the pz orbitals are at 90 degrees from each other. So if the orbital's at 90 degrees and you have overlapping orbitals to form bonds, if you have a hydrogen atom with an s orbital, and that's overlapping with another atom that with one of its p orbitals, and you got 2 of those hydrogen atoms overlapping with 2 p orbitals, if the p orbitals are at 90 degrees, then that means the atoms should be 90 degrees. The molecules themselves, the angle should be 90 degrees. But as we saw in my other videos, um, the angles like 109.4 or 120 degrees, or some of them are 90 degrees, that can't be explained without some sort of other theory. And so the valence bond theory and hybridization is what is explaining the possibility of those other angles. So that brings us to our AXE method. This is a table of the different molecule shapes. So if you see AXE, it means A represents our central atom, X represents the bonded atoms. So we have different bonded atoms. And then your E is going to represent the number of lone pair electrons or electron lone pairs present on the central atom. So we're focused on the central atom, and we want to look at the number of bonded atoms and the number of lone pairs. So the sum of the bonded atoms and the lone pairs, so X and E, the total number of bonding groups, the total number of electron groups, which includes bonding and non-bonding, the lone pairs, this is known as your steric number. So the total number of electron groups is the steric number. And I'll show that in just a moment. So here, this is a table I've shown you in a previous video. So you'll notice that here you have 2 electron groups total. So the total number of electron groups is 2, and you have 2 bonding groups and 0 lone pairs. And so the hybridization of that is sp, and that's because you have a total number of electron groups is 2. They both are bonding. So you need orbitals to allow for the bonding, and so you need 2 hybridized orbitals. And those two hybridized orbitals, as we saw in an earlier slide is that are going to be 180 degrees because of VSEPR, right? So if the electrons are if the electrons are in the two sp hybridized orbitals, then they're going to spread out. They're going to repel each other until they can get as far apart as possible, and that's going to be 180 degrees. So we have the two orbitals overlapping here, and that gives you your linear shape. If you have 3 electron groups, right, so that means that you're going to need 3 hybridized orbitals, because you need orbitals to fill in those electron groups for those electron groups to occupy, and you need that shape. So what's going to happen is you're going to need to take an S and 2 P's, and you're going to hybridize so you can get 3 sp2 hybridized orbitals. So that way you can have those electron groups fill those orbitals. So here's what you see here. So this is your central atom. The pink atom in the middle is your central atom. So you have 3 hybrid orbitals off the central atom here, and you can see that you have this triangular shape. So these atoms here, the orbital from these atoms is overlapping with the hybrid orbital of the central atom, forming the bond. And so you get this trigonal planar structure. And for the molecule that has 1 lone pair, if the molecule has 2 bonding pairs and 2 lone pair, or 1 lone pair, it's still sp2 hybridized, because the lone pair here is occupying one of the hybrid orbitals. So you get the bent shape, right? Same thing with electron group 4. Again, electron groups is the same as steric number. It's the total number of bonding and non-bonding groups, or electron pairs. So here you have 4 bonding groups, no lone pairs. And so again, you need, if you got 4 groups, you're going to need orbitals so that those electron groups can be put into those orbitals. So you need 4 equal energy sp3 hybridized orbitals. And so because you have 4, those electrons are going to have to spread around or repel each other to get as much space as possible. And that is possible only with the tetrahedral structure. So you can see here that this molecule has a tetrahedral structure, and you can see that with the 4 bonded atoms. Here you can see that you have 3 bonded atoms and 1 lone pair, and you can see that the atom here in the top one is missing, but there's a lone pair there. So these 3 other atoms are being pushed down towards the bottom part of the molecule. And so you get a trigonal pyramidal shape. And so here you can see the bent, because this has 2 lone pairs. This would be like water, right? Water had 2 lone pairs, 2 bonding pairs, and so you get this bent shape. But it's bent because you have 2 lone pairs here that aren't being shown. So the electron group geometry is tetrahedral, but the shape of the molecule, the molecular geometry, is bent. So the other thing I want to point out is this AXE. Remember, A is the central atom, X is the bonded atoms to your central atom, and then E is the number of lone pairs. Okay, so that's what we mean by AXE labeling. So your steric number is here. Again, as I mentioned, this is your steric number. Steric number is the number of bonding and non-bonding groups total. So here we have 2 electron groups. Here you have 3 electron groups, 4. So the steric number is 2, 3, and 4. And your X is your bonding groups, right? So here we have 3 bonding groups, 0 lone pairs, 2 bonding groups, 1 lone pair, but the total steric number is 3 for both of them. And then E for the non-bonding groups, the lone pairs. This is your generic shape. This means that what's referred as generic shape is the shape that any molecule have according to the total number of electron groups. So whatever the steric number is, that is going to dictate this generic shape, this electron geometry. So if you have if you have a steric number of 2, which means you have 2 electron groups total, then you're going to be linear. If you've got 3 electron groups total, then you're going to be trigonal planar for the electron geometry. And again, it doesn't matter if you have 2 bonding groups or one lone pair, or 3 bonding groups and 0 lone pairs. The total is still 3. So this electron group geometry is the generic shape of the molecule, and that's the same no matter what regarding the electron groups. So here we have 4 electron groups total. And so all of these molecules will have a tetrahedral electron group geometry. Now, their molecular group geometry, or their molecular geometry here, is whatever the shape of the molecule is. So if you're only looking at the atoms and you're ignoring the lone pairs, then that's the actual shape of the molecule. So you'll notice the molecules here on the left. You only see the atoms. You don't see the lone pairs. So whatever that shape is, that's the shape of the molecule. So that's molecular geometry. And that is going to depend on the number of bonding groups and lone pairs. So here you can see for the tetrahedral shape, so you have tetrahedral molecule. So the molecular geometry of this molecule here is tetrahedral because you've got the shape of the molecule. The 4 atoms that are bonded gives you this tetrahedral shape. So the next molecule here, it has 3 bonding groups, but 1 non-bonding group, 1 lone pair. So it's got the steric number 4. So it's got the same number of total groups. So it means that the electron group geometry is going to be tetrahedral still, but the actual shape of the molecule is not tetrahedral. It's something different. So we call that trigonal pyramidal, because the lone pair is pushing these 3 atoms down, making what looks like a pyramid shape. Okay, and so that's what we're looking at here. So that's the difference between molecular geometry and electron geometry. Again, electron group geometry is looking at the total number of groups, and so as long as you have the group number 4 for the steric number, then you're going to have an electron geometry of tetrahedral. The molecular geometry is going to also depend on how many lone pairs you have. So if you have different numbers of lone pairs, you're going to have different molecular geometry. Okay, so the next in here is 5 and 6. So we didn't talk about d orbitals, but you'll see here the hybridization trigonal bipyramidal, that's sp3d hybridized. So what that means is you're bringing in a d orbital, so that way you can get now 5 different hybrid orbitals. So that will allow an atom to have 5 bonds. Now, this should sound strange to you because we have talked about the octet rule, and the octet rule says that atoms want to have a full octet, so they're only going to form 4 bonds. And that is typically the case, but when you have d orbitals, especially for things like transition elements and anything beyond period 3 on your periodic table, they have d orbitals available. So there is the possibility of having more orbitals hybridized, and therefore you get more hybrid orbitals that can bond. And so this would form other shapes. So here's an example of where you could have a shape called the trigonal bipyramidal, and you have 5 bonded atoms. And so the total number of groups is 5, which means that the central atom now has 10 electrons around it. And so that means that it has more than the octet. Octet is 8. Everyone should be happy with 8, and that's the normal for 4 bonds. But because you have because you have this d orbital here, that d orbital allows you to increase the number of bonds, and therefore you have more than 4 bonds or 4 electron groups around your central atom. And so this is called expanding the octet. And this is allowed because you have d orbitals available that can hybridize and then increase the number of hybrid orbitals. So you can remember the number of orbitals, the number of unhybrid orbitals that you put together and hybridize, that's the same number of hybrid orbitals you get. So since we're taking 5 unhybridized orbitals and we're making hybrid orbitals from them, we get 5 hybrid orbitals, and that's where the electrons are put. And so again, because of VSEPR theory, the electrons want to be as far apart as possible, so they're going to form these shapes in order to give space. And remember, the lone pair electrons want more space. So they're going to take positions that allow for more space. And so again, we have the octahedral. This is where the hybridization of the octahedral shape is where you take 6 atoms. So 6 atoms are going to be bonded to your central atom. So that means you need 6 orbitals. You need 6 hybrid orbitals to bond or keep the 6 groups of atoms. So that means you're going to need another d orbital. So this is called sp3d2 hybridization. So the orbitals you get here are a result of having 1s, 3p, and 2d orbitals hybridized together, and you spit out 6 equal energy sp3d2 hybrid orbitals. And so you can get this shape here. And again, you have an expanded octet. You have 12 electrons because you have 6 atoms bonded. Each bond has 2 electrons, so that means you have a total of 12 electrons. That's beyond the 8. And so again, this is possible with elements that have more than that are in period 3 and beyond. And so you get these shapes here. And so I just want to kind of put together that the hybridization, the orbitals you have, allows for the shapes to take place, because when you have the 5 equal energy hybrid orbitals, those hybrid orbitals are equal energy, and so the electrons that are put into them, they can move and spread around in those orbitals to create enough space. So they want to minimize the repulsion, and so this is why they have these shapes. And so I had gone into more detail in a previous video, but I just wanted to, in this video, kind of talk about hybridization of the orbitals and link that with the shape. So you can see here, octahedral has 6 bonding groups. That means you need 6 orbitals, which means you need 6 hybrid orbitals. And the way you get 6 hybrid orbitals is you take your s, your p, 3p orbitals, and your 2d orbitals, and you hybridize them, and you get 6 hybrid orbitals. In order to get this molecule, to get this shape, in order to bond 5 atoms or have 5 electron groups around your central atom, you're going to need 5 hybrid orbitals. And so that's why you take the s and the p3, you take your 3p orbitals and 1 d orbital, and you hybridize them, and you get 5 equal energy hybrid orbitals. And then you can those orbitals can spread around and minimize the repulsive forces of your electron groups. Okay, and here's another table that I've shown before, and so I won't dwell on this too long. And so here's a couple of videos. If you want to see more, there's a great hybridization video here, and then there's an online 3D shape simulation. I hope you like this video. If you like this video, please hit that like button, subscribe to my channel, hit that notification bell, and make a comment in the comment section. Thanks for joining me. Have a great day.